감사합니다. 일본의 인벤시스네 히로하마라고 하겠습니다. Thank you very much. And, it is a great pleasure for me to give a presentation at this famous KICHE spring meeting. Today I'd like to talk about prediction of additive effect on flue gas desulfurization using versatile process simulators. Today I'd like to talk with the objective of this work at first. After that, we'd like to show our proposed approach and the results of the approach. And finally, we'd like to conclude, summarize some conclusions. Today, as many of you know, that demand of energy keeps increasing very rapidly because of growing up of new economic powers like China or India. But the good oils from Middle East decreases. So we need to find out some alternative fuels like super heavy oil or low-grade coal. But as you know, using these fuels cause SO2 emission. So that research and development and engineering works for flue gas desulfurization are needed, as described in the previous presentation. Most cost-effective flue gas desulfurization method is limestone wet scrubber in many cases. A merit of this system is the low price of the feedstock, limestone, soaking. And we can sell the byproduct, gypsum, to the market. So we can make money with this system. The demerit of this system is the low solubility of limestone in water that causes a large circulation rate required for flue gas desulfurization. To overcome this demerit, we often add some buffer component into liquid to increase the calcium ion concentration in this solution. The buffer component is often become a double base acid, like adipic acid like this. This kind of double base acid has strong buffer effect at operating range of pH of flue gas desulfurization. The addition of this kind of buffer component has strong effect not only on the solubility of sulfur dioxide, but also the mass transfer rate at the interface of gas-liquid interface. Without adding when we add a buffer component, we can sustain the pH of the liquid at the interface, nearby gas-liquid interface, to low level, to high level, so that we can sustain the concentration of sulfur dioxide at the interface at high level. That means that we can have a large driving force for the absorption of sulfur dioxide into the liquid. When we conduct some simulation on the flue gas desulfurization, we need to consider mass transfer. You know, when you apply a traditional theoretical stage model to this kind of flue gas desulfurization, the theoretical stage number is often less than 1. And we need to consider electrolyte equilibrium at the interface. The K value must be calculated using the interface condition, not the bulk liquid condition. Because of these difficulties, flue gas desulfurization unit has not been implemented on many versatile process simulators like Flue, Aspen, or Hayashi. However, we need to simulate flue gas desulfurization unit for engineering purpose. The design and optimization of flue gas desulfurization unit requires material balance and heat balance can be calculated for design and optimization. In 1980s, many experimental run was made for that purpose. Heat balance and material balance were experimentally measured in all the ages. However, now we are running out of engineering sources. Many of engineering companies in the world are fully sold out. People are so busy. So this kind of fully empirical approach by pilot plant can cost a lot. This means that we need some simulator for design purposes. And if possible, it's much better to conduct simulation using versatile process simulators like Flue or Aspen or Hayashi. So this time we tried to equip a versatile process simulator with flue gas desulfurization unit. Now I'd like to talk about our proposed approach. This time we used rate flag in combination with process simulator Flue. Flue is a versatile process, steady-state process simulator, which is widely used in petroleum and chemical industry in all over the world. Flue enables users to build simulation models on interactive graphical user interface very easily. Flue is equipped with most of major unit operations, and large number of parameter data banks were available. Flue can handle not only normal components but also petroleum components. So user can get material balance and heat balance very easily using Flue if flue gas desulfurization unit is implemented on Flue. Now rate flag is embedded on Flue. Rate flag is a rigorously based, rate-based distillation model made by Kubota. Rate flag solves trying and packing towers using heat and mass transfer models for vapor side and liquid side at the same time. Different temperatures for bulk liquid and bulk vapor and vapor liquid interface are assumed. Vapor liquid equilibrium is assumed only at the interface. Rate flag uses rigorous treatment of multi-component mass transfer using a Maxwell-Stefan approach. In the conventional fixed rho approach, the driving force at the interface is described by the difference between composition of single component. However, in rate flag instead, the driving force is described by the difference between composition vector, not the scalar. And the intervention between components can be considered by matrix, not scalar, matrix mass transfer coefficient. Rate flag already has correlation equations for mass transfer, heat transfer, and interfacial area for many kinds of structure packing, random packing, and many kinds of shipper trays. This figure shows architecture of Flue and rate flag connection. Flue can call rate flag, and rate flag calls rate constant calculation programs. Not only built-in programs, we can use user-added subroutine for rate constant calculation. Flue and rate flag calls physical property estimation modules, and here also we can add user-added program for physical property estimation. So this time, we'd like to add our own electrolyte module as a user-added program for physical property estimation. And also we add our own mass transfer model at rate constant calculation. The next, I'd like to show the result of this approach. At first, we made our own small user-added electrolyte model that contains vapor liquid equilibrium, the first and the second dissociation of sulfur dioxide, the dissociations of carbon dioxide, and the dissociation of adipic acid as buffer components. These are the equilibrium equations, and these are material balance of all species, and also we will charge balance for ionic species. All of these equations are solved simultaneously. This figure shows the accuracy of our small electrolyte module attached to electrolyte. Dotted point shows rigorous calculation conducted by OLI electrolyte module that is almost same with the experimental points. From this figure, it is obvious that our small electrolyte module can have almost the same accuracy with OLI module. And also, this module describes buffer effect very well. The next slide shows our own mass transfer correlation. This is based on Onda's equation, and there are two empirical factors for gas phase and liquid phase. These electrolyte models and mass transfer model was implemented on DLLs, which can work with Flue. Implementing these DLLs, if you open Flue, you can find user-added electrolyte model, and you can select this one on the graphical user interface. You can also select the user-added module for mass transfer on the GUI, which open by double-clicking CAM unit. Now we'd like to compare the result of this simulation with experimental data. This experiment was done by EPA of the United States. Liquid gas ratio was 8 liters per cubic meter, and inlet sulfur dioxide concentration was 2,800 ppm. The pH of the solution was 1.0, and temperature was set 445 centigrade. This is a model implemented on Flue. The absorber was modeled as the red flag current. The points are experimental data of pilot plants. When you use traditional theoretical stage model, the calculation result is much different from the experimental data. If you apply Markov tray efficiency, traditional tray efficiency, the result becomes much better, but still not enough accuracy for design purposes. Now, red flag is applied. We can get sufficient accuracy for design and optimization of the process, only using the two parameters for mass transfer, each of liquid and gas phases. And from the red flag calculation result, in low concentration of buffer component, it was obvious that the liquid phase mass transfer dominates these results. And when the concentration becomes higher, the gas phase mass transfer dominates the sulfur dioxide removal. By the calculation of rate flag, you can also obtain the pH profile in the curve. As you expect, pH at the interface of gas-liquid contact is much less than the pH at the bulk liquid. However, if you add buffer component, the difference between the pH difference between the gas and liquid become much smaller. You can also calculate the temperature profile in the rate flag. Because rate flag assumes different temperatures for bulk liquid, interface, and bulk gas phase, we can consider the temperature difference between these phases, especially when vaporization occurs at the same time with absorption occurring. Now, I'd like to summarize the conclusions. A practical electrolyte model for equilibrium and mass transfer coefficient are devised and incorporated into the framework of rate flag embedded on Flue 2. The model successfully predicted the additives with pH buffer effect, which significantly increased the performance of Flue gas desulphurization unit. Thank you very much.